And okay, what is this? This is technically AC power. Okay, question number 1. What is the average of a signal? This is kind of, I'm recalling what you have done. Signal x of t. What is x average? Does anyone know this? Remember this? People starting with A. There is no B, C, D, E, F, G. We jump to H. Harshita will say. Hariharan, Harshita. Essentially, weighted average is a function of time. So you do summation of x of t. Use the time intervals as weight. Okay, so the total sigma dt, okay, technically is the time period if it's oscillating. So we do this with respect to t, and typically x of t is continuous, so we also do this 0 to t. This is the average. Essentially, it's an average, okay, by definition. Weighted with respect to time intervals, okay. Let me write it slightly better typographically. This is 1 by t 0 to t x of t dt. This is your average value. Let's also do one more thing. X RMS. So I think Isha knew the average value. So we'll now ask her, what is this RMS value? Isha, Madhurima, the also could join. When things are positive, negative, sometimes this integral positive area, negative area tends to get cancelled. So sometimes we do this. We square things and average. All right. So this is average of x square of t. Typically, deviations, errors, and all that square makes very good sense. In this case, we squared it. Okay. There is a dt here, right? So to normalize it, you have to put a 1 over t here. So the units of this is square of x. Dimensions of this is square of the signal. To undo that, you will have to take square root. Okay. So let me write this down properly. So this is just RMS value x square dt. This again is averaged. Typically, if it's a sinusoidal or periodic signal, this is averaged with respect to time. Okay, and then we undo the square. This is your RMS value. T is time period. Now, people in my here home, I have an office room, so but the next room and all that is now home. They kind of now they are learning. They are telepathy. They are communicating through some sort of EM radiation, I suppose, because it kind of passed through all this wall and all that. Because I was hoping someone I know, I was just thinking I forget the water bottle, then it comes to my table. Fine. Anyway, so let's go to the next one. Let's ask a simple question. Let's say your x of t, this is x naught. You could call that as a peak. Okay. As a peak value, that into cos omega t. Okay, yeah, Madhurima wrote 1 by t integrate 0 to t x square dt. Yeah, the only issue that is, notice the dimensions dt will cancel. The square root and square cancels. If you take the t outside of it, dt dimensions won't cancel. So at the end of the day, in the LHS, you have dimensions is that of signal. So the RHS, the net dimension should be that of signal. So that was a quick way to, yeah, you missed that, but that's a quick way to correct it. Okay, fine. So x of t is this. So it's a sinusoid. It's oscillating, right? Does anyone remember what is the RMS of this? You can write it in terms of peak. It's a function of peak. Depends on the peak value. Does anyone know that? We did it. We did it for half cycles and things like that. This is a full cycle RMS. So this is cos omega t. If you know this, I'm sure. Niranjana, Neha, Niranjana, Rita, Sayun, and we'll add some. Wait, we'll also add Shivangi. Niranjana, Rita, Sayun, Shivangi, Neha. Does any of you remember what is this RMS value here? You can write it as a function of peak. Yeah, excellent. Okay, now thanks, Madhurima. So this is 1 over square root of the peak value. Let me put that in simple English. Okay, it's a fraction. What is that fraction? Let's see. Square root of 2 is 1.414. 1 over that as 0.707. Okay, fraction of peak value. Going near 0 many of the time. That fraction specifically is 1 over square root of 2. This happens to be 0.707. Great. Yeah, this is 1 by square root of 2. Now Niranjana was wondering whether this is V max by 2. Yeah, you are close, but that is for the next question. You are answering the next question, not this question. Or the next question, you are answering that. Okay, fine. Fourth one. Let's start with something very, very simple. If V of t is peak value into cos omega t, T of t, let's use some colors, contrast. T of t. See, actually, many of the things I am doing, you will start appreciating that when we do medical imaging, image formation, because this is a good way to emphasize signal and things like that. Okay. So cos omega t. Let's also put a n omega t. Power of t. This is a function of time. Of t. Sorry. V of t. I of t. Now this is a definition of power. Instantaneous value of voltage into instantaneous value of current. That's a T, okay. So there is a if I am following it apart with it, then your P of T would be spot. So Shraddha, Sri Krishna is attending. Vaidehi Vaishnavi. So one of you, I suppose, will certainly answer this. We did some integral. So this is okay. P of t is this. Okay, let's not simplify this. So P of t, I wrote down that. What I actually want is, sorry, what I want is, what is average power? Okay, P of t is just product of those two. Then you can use cos product to some formula, but average is integral 0 to t x of t dt or no. What should it be? Okay, so many of you are like again close. Vaishnavi, Shraddha. Okay, let's open anyone. Of t, I of t cos theta. Yeah, so now Shraddha did, that is correct, Shraddha. So you're answering what is P of t, right? So I'm asking what is P average. Do P of t and then take average of that. What should that be? And technically you can say that in just like that you can say the answer. Vi by 2, Vi by 2. So notice I highlighted n for a specific reason. I'm not asking V cos omega t, I cos omega t. I am putting V cos omega t and then there is an integer multiple where n is an integer. I didn't say that, but okay. N is an integer. Now, anyone? What we refer to as orthogonal. The integrals are all zero. Full period integrals are all zero. What is zero? What is zero? We did many things, right? Cos omega t, cos n omega t will be two sinusoids that will be periodic in t, in time period t. So this again will be a zero. In English or some mathematical English, this is omega is fundamental, n omega is like harmonics, upper higher note. Okay, so the fundamental and harmonics, they are all, yeah, n is an integer. Yeah, the Shraddha, now that's I put it there, n is an integer not equal to 1. I technically should say that. That's correct. Only it will be orthogonal. Okay, n is an integer not equal to 1. In that case, this becomes 0. Very good. At least Shraddha kind of. See, notice. No interference, that is, this signal will not affect that signal, this current will not affect that voltage. Difference between V and I of different frequencies. If there is any power, it has to be the same frequency. Cannot be of a different frequency. See, also I am writing this all down because we have done all the primer, right? All that integral trigonometry we have done. So I'm just, today I'm writing down the results. Okay. So if the frequencies are different, okay. Actually, technically, under certain conditions, asymptotically, even n need not be an integer. If you do take an integral over a sufficiently long time interval, Any two frequencies power will be 0, okay, or sufficiently long time intervals. But in this case, the n is an integer not equal to 1, it's certainly 0. This we have to know. Now finally, let's ask a question that all of you would answer, because all of you were answering that. Let's get some gain some momentum. P of t is t cos omega t. I of t is I cos omega t. Thus, then the average. So this is of the same frequency. What is this? Q. Open question. Most of you could answer. Let's see who answers. Same frequencies, there will be power. Else, there is no power here, and there is no power anywhere. Okay. This is non-zero. Shri Krishna, what do you think is the answer for this? So now you shifted your position. I'm telling you, these are same frequencies. These are not. This is the case. N equals 1 case. Frequency. If there is no power here, there is no power anywhere in the world. Okay. Even in the quantum world, there wouldn't be any power. There is nothing going on. Okay. So there better be at least power in this case. Yeah. This most of you answered correctly. Great. This is, yeah. Question I should have asked pages back, because many of you are answering that back then. Notice this, you could write this as V by root 2 into I by root 2. So you could also write this as V RMS, V RMS, your average power. V and I are peak values, then I RMS. This is essentially V by root 2 is RMS. Same frequency, this is the power. So notice, even I think gate 2025, they asked a question from this. They gave two different frequencies. So there is not going to be any power. There will be only one term. Just multiply the coefficients. Typically, peak values are given. The signals are given. The peak values show there are peaks. So just divide by 2, you should get the power. So let's put a slight twist here. E of t equals E cos omega t. I of t equals cos omega t. Now this is the same question. So what is the point of asking it? I will slightly change it. I'll add a phase. Phase as a phase of theta v. Current as a phase of theta I. And what is P average? This also we have done. I'm sure most of you would have forgotten it. Can anyone quickly do product to some formula? There will be two integral with two terms. One term will be 0. Other term will easily simplify if you apply sum to product. Cos A cos B is half of cos A minus B plus cos A plus B. Cos A plus B, that's again a sinusoidal, will disappear. Cos A minus B, this term will cancel this term. What will be left is, suppose if it's not a function of time at all, omega t will cancel. Theta v minus theta I will be there. It's a constant. So cos of theta v minus theta I, integral of that averaged over a time period t. So in the exam, this is what, even if we had forgotten it, if we had product to some formula, you could have technically written down the answer right now and recognizing, hey, there is a constant and then there is a sinusoidal, whose, the sinusoidal integral will be 0. Constant integral fairly easy, pull out the constant. Okay. Because we have done this, I'm just going to write down the answer. This again is going to be Vi by 2. There will be a constant term. Cos theta v minus theta I will be there. Cos A minus B. Cos A plus B will be sinusoidal. It will be a function of time, oscillating. It will cancel. Integral will be 0. This integral is a constant, pull it out, it will remain. And this, you could also write this as I think I did derive this, okay? Consider this at least. Compare and contrast, that's Vi by 2, there will be a Vi by 2 cos theta v minus by 2. Does anyone agree? Is there anyone who kind of see who can read between the lines here? That is, I have not shown the derivation. I did show the derivation not today, but I did show it one of the primer classes. Does anyone recognize this? Notice cos A plus B will be this. So this function will be half of cos of omega t plus theta v minus omega t minus theta I. Okay. So this is a constant. And then there will be one more term plus cos of 2 omega t plus theta v plus theta I. Okay. When you integrate it, 1 by t is 0 to t, right? This is a sinusoidal, this will be 0. And there is a constant. Pull it out. This half showed up here. Then the t and t will cancel. What is left is cos theta v minus theta I. I've also shown you the definition, derivation. Okay. So this is interesting. What it says is, that is, if voltage and current are in phase, average power is Vi by 2. But in any real circuit, this is true only in one case. Okay, can anyone tell me, at least guess this? What kind of a circuit is this? Current and voltage will be in phase. A specific circuit, only a specific circuit is capable of doing this. It's purely resistive. If there is a capacitor inductor, they two cancel each other. Impedance is purely real. There is no imaginary part. Total impedance of the circuit. Yeah, that is very good. That is the only case in which current and voltage will be in phase. So Vi by 2. In that case, it's VRMS, IRMS. So any real circuit, this is VRMS, IRMS, volt voltage and current will have a phase difference. Now comes the question, what will be the phase difference? Like capacitive circuit, phase difference will be 90 degree. Inductive again plus or minus 90 degree. That we saw. In any RC or RL circuit, it will be an angle between zero, minus 90 to 90. That is why this term comes. Okay, so let's also analyze that. Let's look at 3 cases. Now let's draw some lines. This is to structure, at least give it some structure. Technically 2 is enough. Let's put one more line. Three things that we want to compare are C. What shows up there is theta V minus theta I. So let's write theta V minus theta I. Okay. And theta V minus theta I, this is 0 in this case. How about RC? Is it positive or negative? Again, which is where there is this mnemonic, right? Civil. Current leads voltage, current lags voltage. So voltage leads in this case. So in this case, capacitor, current leads voltage. Theta I is higher. So this is less than 0 because current leads, theta high is bigger number, theta V is smaller. So the difference is less than 0. Vector does the other way around. Current lags. Let's also write that. It's just a mnemonic, let's put it somewhere else. Can put it over here also. In a capacitor, current leads voltage. Okay. I leads V. So what do we? Yeah, let's also write that down. E with respect to V. This is in phase. Here current leads. I comes first. Okay. Here current with respect to voltage lags. Yeah, that's correct. So for nothing silly, things are straightforward. So now this is the average power. Again, to give you an analogy, VI, this product is what? The amount of time you spend reading or practicing. And then this accounts for all the distractions and things like that. Distractions. And then whether you're staring at a solution or you're solving and trying to get the solution, right? So all those is there in the second factor, cos theta V minus theta I. This is the seemingly like amount of time and effort that you put in, right? It could be seen that way. So question is, so this is what, in fact, let's not make it one more question. This is what an actual voltmeter sorry, not a voltmeter, ammeter that will measure voltage current. This is what an actual wattmeter, right? How much power is consumed in a circuit will be given by this. Okay, if you put a watt meter, this is what it measures. Okay, and this is, leads, lag, fine. Sometimes let's call this leading and lagging. This is what, in fact, I recapped, right? So now, so this is what your wattmeter measures. Now we have to differentiate it from other things. Now your eighth one. This is the new part that we are learning today. And I'll just give the definitions, okay? And I will also make it simple. So eighth one. For different powers. So there is VRMS, IRMS. This is the amount of time you put in, that is the amount of learning you think you are doing. Obviously, right? This is hard work. It's apparent power. But there is always this efficiency factor involved. Real learning is slightly lesser. It's always a fraction of the amount of time that you put in. It's a fraction. Not very surprisingly, this obvious thing, or this seemingly obvious apparent thing, the real thing is a fraction. What a wattmeter measures, of course, the best function we have for a fraction is cosine is a number between -1 to 1. It's a real power. This is what your wattmeter would read. What a wattmeter reads. And this is also this is what a wattmeter reads. This is the real deal. And notice this is a fraction. This term is a fraction. So the apparent power is getting multiplied by a factor, efficiency factor. In this case, we call that the power factor. Fraction, this is referred to as the power factor. Efficiency factor. This is like efficiency, right? This is actually a measure of resistiveness. The thing is, with a capacitor, it's like a spring. What you put in, you get back the energy. With a resistor, it gets wasted up. This is the only power that gets consumed. In an inductor capacitor, it takes in and then it gives it back. It's like a spring and mass. It's either potential energy or kinetic energy. This resistive thing is like now heat. It just wastes. There is, at least right now, in fact, last week there was a paper. You can go beyond Carnot efficiency using some quantum mechanical effects. But right now for gate biomedical exam, this resistive thing, this is consumed. There is no way you can get it back. How resistive is it? Reality with respect to consumption. Okay. Apparent power VRMS IRMS. Real power is VRMS IRMS cos theta V minus theta I. Power factor cos theta V minus theta I. There is one more last thing. Now calculations are made simple if you consider the imaginary part I said is reactance, right? It's not necessary, so I'm going to write it down. Notice if you're Z, this is R plus JX. This is referred to as a reactance. So this is resistive and this is reactive. So for mathematical purposes, it helps to see, again, impedance as a complex number. So again, for mathematical purposes, we will also bring in one more term here. That is a reactive power. This is, let's say, for mathematical convenience. This is VRMS, IRMS, sine of theta V minus theta I. This is so chosen such that a real power and a reactive power are perpendicular. This is cos theta, this is sine theta. So if you square this, add up Pythagoras theorem, this is perpendicular. In fact, notice, in fact, if you apply Pythagoras theorem, real power square plus reactive power square gives you apparent power square, right? V square I square, V square RMS, V RMS square plus I RMS square, because cos square theta and sin square theta will be 1. So this is for simply for, this simplifies your life if you consider this term. This term simplifies your life. When I say simplifies, this in fact does simplify. Sorry, every time you say it simplifies, there are like 10 more new relations to learn, and then we have to deduce, right? The simplify, supposed to simplify. Okay, I have to correct it. Supposed to simplify your life. Cos also give some symbols, not cos, because symbol, what symbol? Apparent power. So the standard symbols is, this is S, this is P, and this is Q. It's a conventionally, okay, there's a name. Okay, you can quickly note as square plus P square is S, that is in Q form a right triangle, no space, so we'll make the triangle this. A right triangle with hypotenuse. That's it. Apparent power. The moment you have a right triangle, can be represented using imaginary and pure and real and imaginary parts. So you got, write S as P plus JQ. And what I'm referring to here is absolute value of S. So if you consider this complex number, things become easy. But no, this is in fact I would not even like now recommend that. Recognize P and Q form a right triangle. That suffices for our purpose. So it does simplify it. But for completion, let me write that. So your S will be P plus JQ. This is for completion. So now I am going to write a new term here. This is theta V minus theta I. Now let's write down the power factor. Power factor, no, let's not write down the power factor. Let's write down sine of theta V minus theta I. That is, I'm looking at the reactance, reactive power. Okay, I'm looking at Q, sine theta V minus theta I. Can we quickly complete this table? What should it be for? This is easy. What should this be? Sine theta V minus theta I. Great. This is 0 for all. Now, what is this for? C, capacitance. Angle is negative. Theta V minus theta is negative. So this is negative. This is negative. This is positive. Fairly easy. So if you're looking at triangles, leading, the capacitive is leading. Okay, and this is a angle. This is a downward facing triangle. I'll also show that separately. Okay, downward triangle. This is lagging as upward triangle. What do you mean by that? So, let's avoid this math over here. So you got, this is SPQ. Let me at least write down that. Got 2, 2, P, yes, right? This is the hypotenuse. This is the actual power, the cosine of that, and this is the imaginary part. And this is, of course, at right triangles. E, 2. There is an angle theta here. Theta is, by definition, power factor. Units typically important. So let me write down. This is typically SI is volt ampere. SI for this is watt. Notice to differentiate, it's a multiple of voltage and current, they say volt ampere. To say this is power, they say watts. This is volt ampere reactive. VAR. Okay. What is watt? This is apparent. Apparent. Reactive. And then real. Real or true? Okay. Because some of you might find this math somewhat What is this? Repulsive. So now this became triangles. So now that this has become triangles, right now at 8:25, so we'll have to go 10-15 minutes. At least if you have to solve a problem, you have to take 10-15 minutes additional time. But first, let's draw the triangle. Simple drawing exercise. Let's draw. Draw the angle. Power triangle. Okay. First one. For a resistor, how should the triangle look? Guesses? For a resistor, how should this triangle look? For a resistor, Q is 0. S should equal P. Apparent, what you measure, what you show, everything is the same. For a resistor, it should look like this. Purely real. And your theta equals 0. So factor is 1. Efficiency, resistiveness is 1. So the triangle is actually a line in case of a resistor. Theta V minus theta I, they are current and voltage in phase. Sign this term, reactive term is 0. Reactive power term is 0. There is no height to the triangle, there is only a base. The hypotenuse better be equal to the base, which is what I have drawn. How should this look for a capacitor? Let's also put this reference base so that we can draw. Any guesses? How should this look for a capacitor? Pure capacitor. And of course, we also need what the power factor is. So let's also do that for an inductor. First, capacitor. So while I'm waiting for an answer, I am like now saving some time. Make this a table. Fine. It's also fine. Anyone? What is, so the question boils down to what is theta V minus theta I. So you can look at the reactive part. You can look at the height. You can get what the height is from the sine term. So theta V minus theta I is minus 90 degree. So cos theta V minus theta I, that is cos of minus 90, that is 0. Real part is 0. Reactive part is non-zero. That is, there is no base, there is only a height, and this is downwards. There is no base. Only Q. Let me also write it down. There is no true power. And it's pointing downwards because that is sine minus 90 is negative. So capacitor, this is leading power factor is less than 1. Okay, this is leading power factor, but that is showing up downwards. Okay, in fact, for what I have drawn, the power factor technically is -1. Okay, cos of factor is actually 0. Factor, there is no cos theta sine of theta v minus theta I, that is cosine of 90 should be 0. Okay, power factor should also be 0 here, but this is capacitor was leading, inductor is lagging. Again, cos of theta v minus theta I is plus 90. Again, that is cos phase difference is 0. So no true power. What you put in, what the battery puts in, it gets back. What the source puts in, it gets it back. But there is a difference between this and this. Thus, it's technically not a triangle. This again is a line, but it's an upward pointing line. So in all three cases, it's a line. Resistor, only base. Capacitor, negative height. Inductor, positive height. Where am I getting all that from? Cos theta minus, cos phase difference, sine phase difference. Cos and inductor, the phase difference is plus or minus 90 degree. One of them, cos theta, will be 0. Sine theta will be plus 1 or minus 1. From that, I am getting this. Good. We are almost done. I'll just do warm up questions and we'll proceed. But this makes sense? That is not just as a. Does this make sense logically, deductively, from how I defined it? So the phase difference is plus or minus 90. This term is 0. Sine of that will be plus or minus 1. That's it. So let me skip the PYQ because that PYQ solution is already there. But I'll be happy if you could answer 2 questions. Okay, 2 simple questions, 2 follow-up questions. How should a RC element look? RC element. How should it look? It should be RC will be a triangle. This is the first triangle. So far things have been ends. RC will be a triangle. Can anyone at least tell me upward pointing, downward pointing? Resistor, there will be a base. This is a capacitor. It will be a downward pointing triangle. Yeah. So RC element. So by RC, technically it could be this or this. Either it could be this. It could also be this. RC. But here the impedances add up. Here the impedances or harmonically average. So what the imaginary part, real part, imaginary part, that will differ. The power factors will differ, but it's going to be a downward facing triangle. Last thing, for a LR circuit, again let's put a base. LR? This is the last question for the day. Now, in fact, many of you are guessing this should be upward facing because now inductor will have this, make the triangle upward. Here, power factor, this has to do with this cos of that angle. Cos of that angle will be positive, but less than 1. Power factor, cos of that angle will again be, power factor will be less than 1. That is, it's not purely resistive. Okay, does this. Already, actually, we started doing some things. We went from here to here. We did something intuitively straightforward. We added the base. So yellow base length plus this base is 0. We added the length of the bases. We had the heights together for the combined thing. So the bases and heights of the triangles could be added and subtracted. So now for calculations, numericals, bases of these triangles be added. Bases and heights of this triangle could be added and bases and heights of these triangles could be added or subtracted. Added or subtracted respectively. You cannot add the hypotenuse, only the bases, purely resistive parts you can add together, purely capacitive inductive parts will cancel. You can do that, okay? Or subtract respectively, bases and heights respectively. Okay, now this is kind of scheduled time. To do a numerical, I need 10 more minutes. Should we continue? Or there is one numerical that is there and you all could watch it. Do it based on continue with PYQ numerical, which means 10 more minutes, or stop here. Continue right now. Because by the time I finish the numerical, I show up here. No one is sitting. I'm the only one sitting. Right? We don't want that scenario. So let's. Okay, so minority don't continue. There is always this minority. But majority continue, so we'll continue. Okay, minority, this is there in the in 2020 PYQ solution discussion. You could go watch it, but right now I'm going to continue. So let's pull up the PYQ circuits. So 10 more minutes, okay? It's solvable in less than 5 minutes. You're adding and subtracting sides. The explanation say 5 more minutes. Datta. Okay, great. This is open. So notice batsman is not like, it doesn't feel like extra work. Batsman don't like, no, okay, I will accept I am out, right? That is, umpire gave not out, but I will accept out, I'll walk in, right? Unless some show of sportsmanship, typically it doesn't happen, right? So batsman want to continue playing. Oh, okay, I am old, I will retire. Batsman will not say that, right? Because so like that, many teachers that many teachers who taught me, they don't like to stop the class. They like to continue. Okay, so that is somewhat contagious, and I also caught it. So notice actually we did it here. We did this example, right? So here you can look at it impedance wise. So what it says is, so the impedance has a resistive part and a reactive part. Can you make the change the sign of the reactive part? So what was minus 16.5? What was the leading power factor? What was somewhat capacitive? The capacitor was dominating. So can you put an inductor and make it lagging? Can you make the triangle point upwards? That is what they actually asked it here. But let's do it clearly here. Loads are connected. AC supply mains as depicted in the figure. One load draws 10 kilowatt hour. So let me write down, this is real kilowatt. That is true or real. And other load kVA is operating at a power factor. Notice 0.6. Cos of that triangle angle is 0.6. To achieve an overall power factor of 0.9544 lagging. Right now, this is 0.6 lagging. You have to mute it down. You have to modulate it to 0.95. It becomes close to a resistor, right? The nearest kVA rating of a capacitor bank. So this is lagging. That is, this is now behaving like inductor. This is actually inductive. Still wanted lagging, but this is now less inductive. Factor is close to 1. Notice, so this is less inductive. How do you correct an inductor? Adding a capacitor. So typically you add it in parallel. Okay, what is the value of the C? That is what they are asking. Okay, but let's do this graphically so that it becomes fairly easy. And I'll also illustrate this adding and subtracting sides. Resistor 10 kilowatt. Okay, and there is a triangle 0. Power factor. So notice that is operating at 10 kilowatt ampere. So that is the apparent power. Hypotenuse is 10 kilowatt ampere. Okay. And the power factor is given, that is 0.6. So cos theta is 0.6. That means the base will be 10 cos theta, that is 6 kilowatt. Because by definition, power factor is ratio of real by apparent. So 6 by 10 equals 0.6. You can complete this bit over here. In fact, what is this bit? Can anyone tell me what is this bit? What is a reactive bit here? This is lagging, so I have drawn it upward facing. How much is that? You can say that it's one line. Because this is the right triangle, this is square root of 10 square minus 6 square, that is 8. So that value is 8. So there is a resistive, purely resistive element, and then there is a resistor LR element. Okay, there is a resistive element and there is a LR element. Circuit has that. Now you put together in parallel, you just add the sides of the triangles. So when you add these two in parallel, the triangle sides add up. The base and base adds up. The heights and heights add up. The base is 10 and 10. Sorry, 10 and 6. 10 and 6. So the base and base adds up to 16 kilowatt. One height is 0. Other height is 8. 8 watt. This is 8 volt amp reactive. Okay, 8 and 0 adds up and it's an 8. Now, how much is this? How much is this? Because this is a right triangle, again, because it's always a complex number. It doesn't become all of a sudden uncomplex number. Right triangle, can you tell me what the hypotenuse is? Someone answered the height is 8. Great. I need the hypotenuse. So the person who voted, minority who voted no, they knew probably it's not going to be 10 minutes. They sensed something fishy. This fellow is also like his professors that he was commenting. He will not finish it on time. Or he would like to keep continuing, right? Okay, how much is that? Hey, it's a right triangle. You know the base, you know the height. You should tell me what the hypotenuse is. Square root of 16 square plus 8 square. 16 square plus 8 square. So due to lack of time, I will have to do this fast. Square root of that, 17.88. In fact, that is kind of immaterial. Okay, so now it says, hey, you have to do something, and hey, can you make this power factor less? Net power factor, overall power factor, can you bring it down? That is, can you convert this triangle into bringing down the power factor? You are decreasing the resistive element. Overall power factor is this by adding a capacitor. So only the height changes. What is the new height? You do not know that. You know the new power factor. The base remains a base. You are not adding a resistor, so the base remains a base. Okay, but you do know the power factor here. The power factor here is given to be 0.9544 lagging. Okay, so the hypotenuse in this case, that hypotenuse technically was not required to solve this. Okay, this hypotenuse rather is important. This hypotenuse, okay, this is by definition 16 by power factor 0.9544. Happens to be 16 divided by 0.9544, 16.76. So that triangle should become a shorter triangle. That is a correction that you are trying to make. And the triangle still remains right. So what is x? And if you tell me x, we are done with the question. Pythagoras theorem. So 16.76 square minus 16 square. Square root of that 5.004. So the height of the new triangle 5 volt amp reactive. So 8 volt amp reactive should become 5 volt amp reactive. So you should add a leading capacitor. It's a negative height, no base, only negative height. leading capacitor, right? What is the correction you are doing? You are bringing it down by -3 of -3 volt amp reactive. This is a correction you are making, or this is a correction that you need to make so that it becomes 0.9544, and that is also your answer that you're trying to solve for. Negative sign here says the capacitor is pointing downwards. No base, height is negative. Okay, so this is way too lagging. Add a leading element and make it close to, decrease the triangle height. That is what they have essentially said. Okay, fine. I have indeed solved the problem. This has already been solved, but this kind of gives a closure to our initial discussion. But this is a good place to stop. Okay, if you have any doubts, let me know. Comments, group, chat, anything. Okay, then we'll discuss. Stop here. Have a good one. Take care. Bye, everyone.